Good afternoon, everyone. How are you all? Am I audible properly? So, our discussion in the previous class was Earth's magnetism. We have discussed that our Earth behaves as a bar magnet, and the most important point was its north pole. The bar magnet Earth behaving as the north pole of that bar magnet is near the south pole of our Earth. So on this note, we are moving further. So now, what we have studied is there are three components of Earth's magnetic field. There were three components of the Earth's magnetic field. What were the three components? Angle of declination, angle of drift, and horizontal component of Earth's magnetic field. I hope you remember it from the previous class. So on this note, I am moving further on today's lecture. What is angle of declination? Okay. I hope you have revised the previous class. So what is angle of declination? First of all, it is denoted by theta. One thing. Next thing is in most of the books or in some other books, you will find it is denoted by some other notation, like someone is denoting it with alpha, someone is denoting with D. So it doesn't matter. You need to stick to any one of that notation. So I am not using theta for angle of declination. What is angle of declination? The angle between, listen to me very carefully, the angle between geographical meridian and magnetic meridian at a place. What is geographical meridian? You need to recall it from the previous class. The vertical plane passing through the geographical axis of the earth at a place. And magnetic meridian, I have discussed already in the previous class. So the angle between geographical meridian and magnetic meridian, the angle between geographical meridian, okay, this is repeated word, and magnetic meridian. This is magnetic meridian at a place. Note down the word at a place is called angle of declination. What does it mean at a place? It means that it depends on the place. Like if you are finding the angle of declination at Delhi, it will be different. And if you are finding it in New York, it will be different. So angle of declination depends on the location at which you are. So one thing is clear here that angle of declination is not a constant thing. It varies depending on your location. Very good. So what you should remember, the angle between geographical meridian and magnetic meridian, this is written wrong. Magnetic meridian is known as angle of declination. It is denoted by theta. Very simple. Moving further. Another component is angle of dip. What is angle of dip? First of all, how we will denote it? We will denote it with some notation alpha. Clear? This is denoted by alpha. Okay. Now listen to me. Look at me. You have a compass which is free to rotate. Now this compass is free to rotate in horizontal plane. Let's suppose this compass is free to rotate in horizontal plane, and as soon as you suspend it freely, it turns in the north and south direction, the geographical, or you can say the geomagnetic north and south direction. So let's suppose it is aligned like this. Clear? Now, what you did, you there is a plane passing through this magnet or through this compass. That plane is known as magnetic meridian. That I have discussed in the previous class. Now I'm repeating the same thing. What is magnetic meridian? You have suspended a magnet freely to move free in horizontal plane. It stops in north-south direction. The vertical plane passing through the magnet is known as magnetic meridian. Now, what you did, you took another magnet and placed this magnet in the same plane. But this time, the magnet is free to move in the vertical plane. The magnet is free to move in the vertical plane, and as soon as you suspend it, it will dip some angle, like it will either dip downward or it will incline upward. So the angle it made with the horizontal is known as angle of dip. I hope the statement is clear. In which plane you are placing the magnet? You are placing the magnet in the magnetic meridian. And in which plane it is free to move? It is free to move in the vertical plane. Then the angle made by the magnet with the horizontal is known as angle of dip. Now you can see all this in this definition. Now what is the definition? You can see it on your screen. The angle made by the magnetic axis of a bar magnet. Clear? Now, which is free to move in vertical plane and lies in the plane of magnetic meridian. All these things I have discussed already. And angle made with what? With the horizontal is called angle of dip. So I will summarize these two things on the next slide. Till now, everything is clear. What is the basis? Why it is declining? Why it is dipping by some angle? It is not horizontal. It is like you know that Earth's magnetic field or any compass or any magnet will try to align in the direction of magnetic field. Always tries to align itself in the direction of magnetic field. That's why the needle will align or the compass or the magnet will align or it will dip or either incline according to the direction of magnetic field. Now we can summarize these things on the next slide, which is our third component of Earth's magnetic field, that is horizontal component of Earth's magnetic field. How it can be viewed, you can see here, like, look at that. Like this is a plane, you can see. And this plane is magnetic meridian. There must be another plane like this, you can see. I hope the diagram is pretty much clear to you. This is another plane, and this plane is geographical meridian. Now listen to me. What's happening? The angle between these two planes is denoted by theta, which is known as angle of declination, which is known as angle of declination. Now, when you suspend a magnet freely in horizontal plane, it will come in the magnetic meridian. When you suspend it freely in the vertical plane, what will happen? It will align, it will dip something or dip by some angle, let's suppose like this. This is the magnet, and this is going to be the north pole of the magnet. I hope it is clear to you. So this is the north pole. So the magnet always aligns in the direction of magnetic field. So this magnet is aligning in the direction of magnetic field. So what I will say that the needle or its axis will indicate the direction of Earth's magnetic field. So this is going to be our Earth's magnetic field BE. And the angle it made with the horizontal is known as angle of dip, denoted by alpha. I hope all these statements are clear. What is theta, what is alpha, and what is Earth's magnetic field? So this is our Earth's magnetic field BE. Now one more thing. You can easily do the components of this Earth's magnetic field. If you can see, this is Earth's magnetic field and this angle is alpha. So this component will be BE cos alpha, and this component will be BE sin alpha. Is it clear? Now you can again see that this BE cos alpha is horizontal. So that's why it is named as magnetic field in the horizontal direction or horizontal component BH, and this is known as vertical component BV. Clear? I hope all these statements are clear. Now you can make some equations. What will be those equations? First equation will be, you can see vertical component is BE sin alpha, equation number one, and horizontal component is BE cos alpha. Is it clear to everyone? Quite visible from the diagram. Now, if you can see, if we divide these two equations, what we will get? We will get vertical component divided by horizontal component is equals to tan alpha. You can either remember this relation or you can transform it in any other format like B vertical is equals to B horizontal multiplied by tan alpha. You can make any relation out of it. Like you can say vertical component is equals to horizontal component into tan alpha. You can remember it like this way, but all these things are similar. What is alpha in this equation? Alpha is the angle of dip. What is B vertical? This is vertical component of Earth's magnetic field. BH is the horizontal component of Earth's magnetic field. All these statements, all these terms are clear to everyone, I hope. Now, one more thing. We got three components of Earth's magnetic field that are important. Now, you can see there are four components that you can see on your screen. One is angle of declination theta. You can see theta is also written on the screen. Alpha is written on the screen. Vertical component and horizontal component. So four quantities are mentioned, out of which only three are required, out of which only three quantities are required to get the magnitude and direction of Earth's magnetic field. That's why Earth's components are generally mentioned as there are only three components, that is theta, alpha, and horizontal. One more relation that we can form from here, if you square 1 and 2, then add, what you will get? B vertical square plus B horizontal square is equals to BE square. You can take common, and what it will be? Sine square alpha plus cos square alpha, which is 1. So here you can conclude that Earth's magnetic field is nothing but vertical component square plus horizontal component square. So now you know the magnitude and direction both of the Earth's magnetic field. This is the magnitude of Earth's magnetic field. And the direction is decided by the angle of dip and the angle of declination. These two components are responsible for the direction. I hope all these statements, all these formulas are clear to you. Now coming back to some punchlines. After that, we will discuss some concept test questions. Punchlines. Before moving towards the punchline, let's see some diagram that we have already discussed. This is our Earth. You have already seen this. And this is our geographical north. This is our geographical south. Near the North Pole, there is magnetic South Pole. I am mentioning it South magnetic, and this is North magnetic. This is clear. Now, another thing that you should focus. These are known as poles. This location, or I will change the color of the pen. This location, any doubt? Okay. This is known as poles, or these locations are known as poles. Now, listen to me very carefully. At these poles, what you can see that Earth's magnetic field is perpendicular to the surface. So, what I am mentioning here, at poles, just try to remember it as it is. At poles, Earth's magnetic field is perpendicular to the surface. To the surface of what? To the surface of the Earth. Clear? That means Earth's magnetic field is vertical. Now listen to me. You are standing at the poles like this with some magnet in your hand. Like suppose this is the magnet in your hand and this is you. And you are standing at the earth surface like here I am standing, and let's suppose there is north pole, there is south pole below my legs, or whatever I say, below my feet there is a south pole of the earth, magnetic south pole I am talking about, obviously. So I am holding a magnet. You can also imagine it with yourself that you have a south pole of the bar magnet, of the earth's bar magnet on below your feet, and you are standing holding with a holding a bar magnet which is free to move in the vertical direction, which is free to move in the vertical direction. So what will happen to it? Its north pole will be attracted towards the south pole, and it will completely dip or become vertical. And the if it becomes vertical, what it will mean? It means that angle of dip at this place, how much angle it is making with the horizontal direction, it is completely dipped by 90 degree. So angle of dip at this place is 90 degree. So what you can conclude is alpha is equals to 90 degree. Where? At poles. I hope clear it is. Now, there might be some other question in some other language, like if you hold a magnet which is free to move in horizontal direction, then what will happen? Now, this magnet the magnetic field is trying to align it in the vertical direction, but this magnet can move only in horizontal direction. So it will not move according to the magnetic field because the magnetic field cannot move it. So it can orient in any direction. It may orient itself in any direction without any problem. I hope this is clear. Now, same thing if I say angle of dip is 90 degree. So at this position or at poles, horizontal component will be what? Can anyone answer? What will be the horizontal component of Earth's magnetic field? All the magnetic field of the earth is vertical. If a vector is in y direction, it has no component in x direction. That means horizontal component will be zero. I hope these 2 points are clear. So what are these? These are the punchlines for the position of poles. Now I will do the same thing at equator. I have answered a lot of questions here. At equator, if I say, where is the equator? You can see this is the equator. This is the position of equator. At equator, magnetic field you can see is parallel to the Earth's surface. So what I say, magnetic field is parallel to the surface. Now again you are holding a bar magnet. This is you standing on the surface and you are holding a bar magnet. Let's change the color of the bar magnet. This magnet is again free to move in the vertical plane. In which direction it will align? You will say, sir, it will align in the direction of the magnetic field. Now, the magnetic field is horizontal, so it will also remain horizontal. So it will also remain horizontal. If it is horizontal, then angle made by it with the horizontal is zero. So again, I will conclude that alpha is equals to zero at this place. And if magnetic field is horizontal, that means there will be no vertical component, because if there is a vector quantity in x direction will have no component in the y direction. So that means vertical component will be zero. These are the punchlines that you should remember. So if I ask you and I'm asking you to hide these things from the screen, and what I will ask, what is the angle of declination at equator? What is the angle of dip at equator? You will say at equator angle of dip will be zero. Angle of dip at poles 90. You should answer very quickly. I hope it is clear. Moving further. You can write down the things, you can write down the important things, you can write down the punchlines. Okay. Should I move further? Yes. Moving further. So now this is a checkpoint where you should answer few questions. The first question on your screen. This is a kind of subjective type question, a very simple concept building question. A magnetic needle free to rotate in a vertical plane. Are you getting my point? It can move in vertical plane. Orients itself with its axis vertical at a certain place. Now it is free to move in a vertical plane and aligns itself vertical like this. What are the values of horizontal component of Earth's field and angle of dip? You have some 30 seconds to answer the question. You have some 30 seconds to answer the question. Anyone got the answer? Okay. Now, according to the question, the needle is free to move in vertical plane like this. It can move in vertical plane. Now it becomes vertical means it becomes like it is free to move in the vertical plane. It orients itself as shown. It becomes vertical. What does it mean? That it is at the poles. It is at the poles. It happens at where? It happens at poles. If it happens at poles, that means angle of dip will be 90 degree. How much it has declined? It has the angle dipped by it with the horizontal direction is 90 degree. So angle of dip is 90 degree. And if angle of dip is 90 degree or the field is vertical, then at this place horizontal component will be zero. I hope you should remember. This is at poles. It happens when the magnet is at poles or you are at poles. So at poles horizontal component will be zero. Moving further for the next question. Again, the angle of dip at poles and the equator respectively are, you got some 20 seconds to answer this question. You can recall it from the punchlines. The same thing I have discussed in the punchline. You have got the same kind of question here. You have some 20 seconds to answer. So the question says the angle of dip at the poles and the equators respectively. What I told you, at the poles angle of dip is 90 degree. Poles alpha is equals to 90 and at equator alpha is equals to 0 degree. Needle becomes horizontal or remains horizontal. At poles, it becomes vertical. So alpha is 90 and 0, which is correct option number B. So you should remember this question. Most preferably, it is asked in the NEET exams lot of times. B is the correct answer. Moving further. Now, again, there is a good question here. What is the question? First of all, you got some 30 seconds of some 40 seconds to read the question. After 40 seconds, I will ask you. Till then, I am also reading the question. A dip circle is taken to a geomagnetic equator. Okay. The needle is allowed to move in vertical plane perpendicular to the magnetic meridian. The needle will stay. One thing that you should know, what is dip circle? Dip circle is used, or the thing that I have discussed you, the angle of dip. In angle of dip or while finding the angle of dip, we have a magnet which is free to move in the vertical plane, which is free to move in the vertical plane. That is known as, so the needle, the arrangement of that needle is known as dip circle. Clear? Now there is a dip circle in the geomagnetic equator. You can see what is geomagnetic equator. If this is our earth, This is magnetic south and north pole, south and north, and this is our magnetic equator. So in the magnetic equator, the needle is allowed to move in a vertical plane. So needle is free to move in the vertical plane, but the magnetic field, everybody knows magnetic field is horizontal at this place. This is magnetic field. Needle can move in the vertical plane, but the magnetic field is try to align it in the horizontal direction. But needle is not free to move in the horizontal direction. Are you getting my point? Just look at me. Let's suppose I have a needle which is free to move in this vertical direction like this. I hope you can see the pen, or if I can change the color of the pen, it is quite visible, I hope. This is the needle which is free to move in the vertical plane like this. But the magnetic field is horizontal, which will try to align it in the horizontal direction, but it can't move in the horizontal direction. So what will happen? This magnetic field will have no effect on the magnet, will have no effect on the magnet. So ultimately, needle will be not under the influence of the magnetic field. So it will remain in any direction. If you release it from this point, it will stay in this direction. If you release it in this point, it will stay in this direction only. So it will not follow the commands of the magnetic field. What it is trying to do, it will do whatever it wants to do. So what I am saying, in any direction it is released, the direction in which you release the magnet, it will stay in that direction only. So which is the correct option? Option number D is correct. Why it is happening? Because the plane in which magnet can move is different from the direction of the magnetic field. So correct option is D. You can check it here. The same kind of question is on the next slide. Go through this slide, go through the question and answer. Again, you got to read the question, you have some 30 seconds. I hope that you got the answer. Question says a compass needle which is allowed to move in horizontal plane. Now mark the word, it is free to move in horizontal plane only. That was the point of discussion from the previous class. I was always discussing these two things, like vertical plane free to move or free to move in horizontal plane. And in every question you will find this thing. So that's what is the importance of these small things. Free to move in the horizontal plane is taken to a geomagnetic pole. Now again the situation is just opposite to the previous one. Now what's happening? This is our earth, okay? And there is a magnet which is free to move in horizontal plane like this. This magnet can move in horizontal plane only. But everybody knows that at the poles, magnetic field is vertical. I hope everybody remembers the same thing. Now, this magnetic field will try to move the magnet in the vertical direction or in its own direction. But magnet can't move in the vertical direction. It is free to move in horizontal direction only. So can I say one thing, that this magnetic field has nothing to do with the magnet? This Earth's magnetic field has nothing to do with the magnet, because my magnet is not going to follow the commands of the magnet, because my magnet is just free to move in the horizontal direction. but magnetic field will try to move it in the vertical direction. So again, it will follow its own command. Whatever it wants to do, it will do. So it will stay in any position. Again, option D is correct. So you need to find out the differences. If I say that magnet is free to move in the vertical plane in this question, what if I say? Then this magnet will be aligned vertically, or it will stay in the vertical direction. Is it clear? Or you can say in the north-south direction. Then the answer was that option A would be correct. But in this situation, option D is correct. Option D is what? This is option D, which is correct answer. Now moving further for the next question. These were the conceptual questions. Now we are moving towards some numerical questions in which we have some numerical value. So you have some, I will say 30 to 40 seconds to answer this question. I will wait for your responses. I am some boy. Your answer is not correct actually. Option B is not correct. You can just check your answer. Don't force me to say something which is not good. Try to solve the question. And after that, I have given you some 40-30 seconds to answer. So there is no need to hurry things out here. Use pen and paper to solve the question. What question says the vertical component of Earth's magnetic field? Okay, they are asking the vertical component is root 3 times the horizontal component. Okay, that means they are saying that vertical component, first of all, what is the relation between vertical and horizontal components? Do you remember anything like that? Vertical component is equals to horizontal components times tan alpha. This is the relation that we know. I have discussed it before 3 or 4 slides. Now vertical component is equals to BH into tan alpha. Now question says vertical component is root 3 times horizontal component. Can you say that vertical component is root 3 times of horizontal component? I have placed this value is equals to BH tan alpha. Now you can cancel BH and BH. So what remains? Root 3 is equals to tan alpha. So what is going to be alpha in this case? Can you answer this one? What is going to be alpha? It is going to be 60 degree, which is correct option number C. Very simple, very much doable, asked in the NEET exam. Moving further. This is another question. For this question, you have some again 40 seconds. try to remember one thing. The Earth's magnetic field might be a very small topic, or you can see that, or you will find in your notebooks or in your books that there are not a lot of questions on this topic, this particular topic coming in the examination. But remember one thing, the questions that were asked from this Earth's magnetism are not from its own chapter. In the next chapter, EMI, there will you will find a lot of questions coming on the concept of Earth's magnetic field. They will include some word like horizontal component. They will include some term like vertical component. They will include some term angle of dip. So lot of terms will be there in the next chapter. So this is not a chapter. This is a concept that will be used in later sections or later chapters. So if you don't know these concepts, then it will be difficult for you to answer in the next chapters as well. So such type of topics which are small and can be used in other chapters, you must you must learn those concepts very well. Okay, I hope that you have read the question. Now I will discuss it. What it says, there is okay, a ship is sailing due east. That means there is a ship which is moving in the east direction. But this east direction is according to a compass, not by the geographical east. They are asking, they are saying according to a compass, it is moving in the east direction. Okay. Now, if the declination at that place is 18-degree east of north, what is declination? The angle between geographical meridian and magnetic meridian. What is magnetic meridian? You must know. What is the true direction of the ship? So for that, let's suppose this is our north and south direction. So definitely this is going to be our east and west direction. Quite clear. Now question says that angle of declination at that place is 18-degree east of north. That means what is the meaning of this declination term? This term tells us that according to the compass, the north direction is 18-degree east of north. If I draw 18-degree east of north, that will be something like that. So according to the compass, this is north direction, according to the compass. And this is definitely going to be the south direction. I hope this thing is clear, and this angle is given as 18 degree. 18-degree east of north. Can you see that this is 18-degree east of north? Now, this declination thing, remark my word, it tells us the direction of magnetic or the north and south declared by the magnet or the compass. Now, if north and south are in this direction, everybody knows that east and west will be perpendicular to it. So, east and west will also be perpendicular to this north and south. And what will be the east and west? These will be the east and west. I have written a term M for the magnet or the compass. So, according to the compass, it is going in the east direction. What is its actual direction? Can you find out now? If according to the compass it is going in the east direction, then actually ship is moving in this direction. And this direction is what? Can you find this angle? If I give you some time, can you find this angle? What will be this angle? Obviously, north and south are shifted towards in the clockwise direction by 18 degree. Like you can see, this is north shifted by 18 degree north in clockwise direction. So east will also shift by 18 degree. So this is 18 degree. So what is going to be the actual direction? 18 degrees south of east. 18 degrees south of east. 18 degrees south of which is option number B. This is our correct answer. 18 degrees south of east. This is the shift. Are you getting my point? I hope it is clear to everyone. If you have any doubt, you can ask. Otherwise, I will move further. So option B is the right answer. Moving further. Okay. You have one more question. Quite simple. We will have some 50 seconds to answer the question. Tell me the correct answer. Or it is not mandatory to answer the correct one. The one that you have attempted, you can answer that one as well. Are you solving the question? You can say yes or no. If you can solve this question or need more time, you can say need more time. Or if you can't solve, you can say no, sir, I can't solve this question. Need help. You can say anything like that. How many of you are JE aspirants and how many of you are NEET aspirants? So if I read the question, what it says, in a magnetic meridian of a certain place, okay, horizontal component of Earth's magnetic field is something 0.25. What is G? Can you tell me what is G here? Can you answer this simple question? What is the meaning of this G? What is this unit G? And the angle of dip is 60 degree. What is the magnetic field of the Earth at this location? Okay. So they have given us angle of dip. They have given us the horizontal component. So you can write out the things. Horizontal component is 0.25. G is okay. Bacha, G is some unit in this case. G is the unit of magnetic field. This is magnetic field and its unit is Gauss. So this is Gauss, which is the unit of magnetic field. And if you don't know, you can remember one more thing, that 1 Gauss is equals to 10 to the power minus 4 Tesla. This is the relation between Gauss and Tesla, where Tesla is the SI unit of magnetic field. Clear? So this field is Gauss, 0.25 Gauss horizontal field is given. Now angle of dip is denoted by alpha, so alpha is given as 60 degree. Clear? Now they are asking the what is the magnetic field. Now everybody knows, or in fact everybody should know, that what is Earth's magnetic field. The relation you can note down on your notebook and keep it in your mind, that Earth's magnetic field, or the magnitude of Earth's magnetic field, is horizontal component square plus vertical component square. Clear? But according to the question, vertical component is not given. So what you will do, just make some changes. This is B horizontal square plus, let me connect the power supply. This is horizontal component, and you know that vertical component is equals to horizontal times tan alpha. Is it clear? Vertical component is equals to horizontal times tan alpha. So you can put this value, and what you will get, BH square tan square alpha. I hope this is clear. Out of this relation, you can take horizontal BH as common, BH square as common. If you take it common, BH will come out of the equation, and what will remain? 1 plus tan square alpha, and alpha is what? 60. Clear? So Earth's magnetic field will be BH under root 1 plus tan 60 is what? Root 3. If you square it, it will become 3. So can you see that this is 2? Root of 4 means 2. So Earth's magnetic field will be 2 times of horizontal component. And 2 times of horizontal component means you can put the values. And if I put the values, Earth's magnetic field will be 2 times of 0.25 Gauss, that is 0.5 Gauss. Is it clear? I hope this is also clear to you. On this note, I'm ending the session. Bye everyone.